Please read the respective topic in your answer here and try to solve this reading quiz. Now let's solve another last problem related to the impact. This is the problem 15-83 in which we are provided with two collars. The mass or the weight of the collar is 10 pounds. It is attached with the spring having stiffness 20 pounds per feet. The unstretched length of the spring is 3 feet. So when this collar A strikes with B, it will move to 4 feet, and we have to determine the velocity of A just after the impact and the force exerted between A and B. Similarly, the time is given, which is 0.002 seconds, and the coefficient of restitution is given. So we have to calculate the force, and we have to determine VA2, right? In order to solve this problem, as there is an impact between A and B, so we can or so we can apply the conservation of momentum and coefficient of restitution equation along this axis. So we know that the conservation of momentum is mass of collar A, velocity of collar A, plus mass of collar B, initial velocity of collar B. Similarly, we have mass of collar A, final velocity of collar B after the impact, and vice versa. So when we solve it, uh, we will have the mass of the collar A, which is 1 divided by 32.2. Similarly, the velocity is unknown to us, plus the initial velocity of collar B is 0. So the final velocity, which is 1 divided by 32.2, VA2 is unknown and we have to find it, right? Plus the mass of the collar B, so this is 10 divided by 32.2, and the final velocity of the collar B is unknown as well, right? So this is our equation 1. Now the coefficient of restitution, we have this is our positive signs. So E, which is 0.5, is equals to, we know the formula, VV2 minus VA2 divided by VA1 minus VB1. So in this case, VB2 is unknown, VA2 is also unknown, whereas this is VB2 minus VA2. VA1 is also unknown, which is VA1 minus VB1 is 0. So this is our equation 2. In order to solve this problem, we need another equation to get the final velocity of this collar B, right? So if we can individually see this collar, so how can we uh, find out the final velocity or the velocity after the impact of this collar B? So over here we can see that when A strikes with B, then its energy will be uh, transferred to B and it will move in the right hand side, and this will stored in this spring. So we can apply the conservation of energy of collar B, and in that equation we can get the velocity of B after the impact. So let's apply the conservation of energy uh, for collar B. So the conservation of energy for collar B is, we know that T1 plus V1 is equals to T2 plus V2, right? So the initial kinetic energy of this collar B, so after the impact, it it is initially at rest, but after the impact it must have some velocity, which after some time uh, will be zero, because it is provided that the caller B will be momentarily at rest, or this, or it stops. So we have initial kinetic energy, which is half m vb vb2 half mv square. This is the velocity of the scholar after the impact, plus the potential energy, which is zero. Now the final kinetic energy of the scholar, it is zero, because it will stop after some time. It has stopped after some time, plus the potential energy. So in this case we have elastic potential energy, which is half kx square. So this is half, k is 20, x is, so it will move to the distance 4. So this is 4, we have this 3. So by Pythagoras theorem we can get 5 over here. So the stretch length is 5 and the unstretched length is 3. So that is why we will have 2 square over here. So when you will solve this, you will get VB2 is equals to 16 feet per second, right? So this is the value which you can put in equation 1 and 2 to get the velocity of this caller A. So after solving the equation, we will get VA1 is equals to 118 feet per second, right? And VA2 will come out to be minus 42.8 feet per second. So these are the values which come out after solving the equation 1 and 2. Now finally we have to find the force. Uh, so for caller B, we can apply the impulse and momentum equation. So we have, this is our positive direction, so we have mv1 plus sum of all the forces, impulses uh, from position from the time t1 to t2 is equals to mv2, right? So for the caller B, it has initial momentum 0 plus the force which is being applied for the time 0.002, right? And this is the final momentum of this caller B. So mass of the caller is uh, 10 divided by 32.2 plus the velocity. So final velocity of this caller is 16, right? So when you solve this problem, you will get F is equals to 2492 pounds, right? So that is how you have calculated the impulse force which is applied by A onto the B. So that is how we can solve such problems. Please go through the slides again and solve this concept quiz. Please also solve this quiz and can discuss if you have any queries in the live session. Now let's solve the last topic of your chapter number 15, which is angular momentum, movement of a force and principle of angular impulse and momentum. So let's move ahead and see that what are the details of this topic. So as for the previous knowledge, we know that the movement of the force m is equals to F into d, right? So F is the force and d is the movement arm, and they are uh, and d is the perpendicular distance to that line of action of the force, right? And similarly, we know that the linear impulse and momentum equation, this is mv1 plus sum of all the impulses fdt from time t1 to t2 is equals to mv2, right? So this is our linear momentum, this is our impulses, linear impulses, and this is our final momentum. What I am doing, I am just multiplying that distance d, perpendicular distance d, by each term in this equation 1, right? So this will become mv1d plus fd from t1 to t2 mv2d, right? So over here you can see that this term will become the moment of the momentum. So as for the moment of the force is F into d, if F is replaced by m into v, which is momentum, then I can term it as moment of the momentum, which is mvd. So this will be your angular, uh, this is your angular momentum, right? And it can be represented by h1, right? Linear momentum is can be denoted as L, whereas angular momentum can be represented by H. Similarly, this is F into Fd, which is the moment. So this term will become the angular impulses, and I can write it as T1 to T2. This will become m dt is equals to H2, right? So this term you can write it as moment of momentum or angular momentum. This term becomes the angular impulses, and this will become the final angular momentum. So this equation 2 is called the principle of angular impulse and momentum. So if our body is moving with some certain pivot point at the perpendicular distance d, so I can apply the principle or equation of angular impulse and momentum in that case. And if and similar with the linear impulse and momentum, if all the impulses of if all the angular impulses in our system will become zero, then our angular momentum will remain conserved. So I can write it as sum of h naught 1 is equals to sum of h naught 2. Where is the h naught is the angular momentum at point O. So this will be the initial angular momentum, and this will be the final angular momentum will remain conserved if all the angular impulses on our particle will become zero. So now let's move ahead and see that how we can apply these concepts to our problems. Okay, one thing I forgot to mention, that we know that if we want to calculate the moment of the force, then it will be F into D by using scalar method. Okay, if I want to calculate it by using a vector method, then moment of the force will be R cross F, right? So if I'm going to calculate the moment of, this is the moment of the force, and if I want to calculate the moment of the momentum, then this will be the H, right? and this will be MVD. So this is the scalar method, and if I want to calculate the angular momentum or the movement of the momentum, then it will be H is equals to R cross MV, right? And this is the method to find out this angular momentum. Now let's go through some problem and see how we can apply the concept of angular momentum to solve the problems. Now let's solve a problem which is F15-24, in which we have two identical spheres having the mass 20 kg, and these spheres are rotating along the point O, right? And on which the force of 10 Newton is applied, and also a couple movement which is 80 Newton per meter. So we have to find out the speed of the spheres after the 4 seconds. So this is our system in which we have two spheres on which some forces are acting, and it is also provided that a couple movement of 80 Newton per meter is applying on this rod. So as our bodies are, or the particles are moving in along a pivot point which is O, so we can apply the uh, principle of angular impulse and momentum in this problem. So let's move ahead and apply the equation to get the velocity of the sphere after 4 seconds. So as we applied the principle of linear impulse and momentum for a particle and a system of particle, so we can also apply the principle of angular impulse and momentum for a particle and for the system of particles. So as over here we have two particles and in our system, so we can apply the equation of sum of all the angular impulses at point A plus all the uh, sum of all the angular momentum, sum of all the angular impulses, which is m naught dt from the time t1 to t2, right? And it is equal to sum of all the uh, angular momentum, final momentum, right? So over here uh, we have this initial angular momentum 0, because it is starting from the rest. So this is 0 plus now let's solve a last problem of chapter number 15, which is 15-111, in which we have a box which is being pulled in a radial direction with some radial velocity 4 feet per second. When it is at point A, it has the velocity which is 15 feet per second, and after some time its radius reduces and it reaches at the radius 1 foot at point B. So we have to calculate the amount of the work which is needed to pull the rope from A to B. And in this problem we have neglected the friction and the size of the box. So as our particle is moving about some pivot point, so in order to calculate the work done, uh, we can apply the principle of work and energy, which involve the term work. So we know that uh, we have T1 plus sum of all the work done from A to B is equals to T2, where T1 and T2 is the initial and final kinetic energy of our particle. So we have to calculate this work done from moving this box from A to B. So this work done moving a box from A to B is T2 minus T1, right? So the final kinetic energy of our box is half mv square, where 8 divided by 32.2 is the mass, and the final velocity is unknown to us, right? So this is vb square. Similarly, minus half, this is 8 divided by 32.2, and we have this initial velocity at the position A, which is 5. So this is 5 square, right? So this is the velocity which is unknown, and in order to solve the work done, we have to first calculate this velocity of the box at point B. So at point B, we can apply the conservation of angular impulse and momentum, because we don't have any external impulses, right? So let's name this equation. So this is our equation 1. Now let's apply the conservation of angular impulse and momentum of our particle at point B. So we have the angular impulse along the moment axis z at point A will be equals to the uh, angular momentum at point B, right? So at point A we have, this is mvd, so we have the mass, which is 8 divided by 32.2, right? We have the velocity, which is 5 feet per second, and we have a distance d, which is 2, right? Similarly, at point B we have the same mass, which is 8 divided by 32.2. We have this distance 1 feet, and we have this velocity which is tangent to that path, right? So this will I can call it as VBT, because this is our radial and transverse axis. This is a polar coordinate system. That is why the component, we have the component of the velocity along the radial and the transverse direction. So when I solve it, I will get this velocity at point B, the tangential component, as 10 feet per second, right? And in order to calculate the velocity, the magnitude of the velocity, I have to apply Pythagoras theorem to get the velocity. So this is Vb. We have 10 square plus the radial component of the velocity, which is constant, and it is uh, 4 feet per second. So this is 4 square. So you will get 10.8 feet per second. So this is the velocity of the box at B. So you can put this value in equation 1 to get the work done, uh, to get the box from position A to B, and you will get the UA to B is 11.3 feet pounds, right? So that is how you can also apply the conservation of angular impulse and momentum to solve the related problems. Please read this topic in webbook and try to solve this reading quiz. Please also go through the slides again and solve this concept quiz. So this is the end of the chapter number 15, which is the kinetics of particle by using impulse and momentum. This is also the end of your uh, uh, dynamics of particles section, in which you have studied that if we are considering our bodies as a particle and we are considering it to have a point mass and we are neglecting its shape and size, then we can perform its kinetics and kinematics analysis. So in this whole portion of your dynamics course, we studied that chapter number 12, which is related to the kinematics of particle, and in that chapter we studied that how we can calculate the kinematic parameter without including the analysis of force in our uh, solution, or uh, we can only interested in finding the velocity, time, acceleration and position of a particle. After that we started chapter number 13, 14 and 15, which are related to the kinetics of particle, and these are the different procedure which you can adopt to solve the problem related to the analysis in which the forces as well as the kinetic parameters are involved. So this is the end of the this dynamics of the particle portion. Now we are going to start chapter number 16, which is the kinetics of the rigid body.